Dear friends, today we will talk about the Cretaceous of Trichinopoly. The east coast of India was formed during Cretaceous period in consequence to separation of India from Antarctica Australia assembly, sometimes referred to as the Great Cenomanian Transgression, around 98 million years. The initial opening of the east coast started in the southern part and gradually progressed northwards. In this process, several coastal basins were formed in which the marine sedimentation started during the Cretaceous period. Here are the important basins from south to north, starting from Kaveri, Pala, Krishna Godavari, Mahanadi and Bengal basin. In the northeast most extremity, Assam basin was formed. Deposits of most of these basins are in subsurface and major part of the basin is in the offshore areas. In some of the basins, thin outcrops of the Cretaceous age are present, especially in Kaveri basin, Pala, Krishna Godavari and Mahanadi basins also. In Kaveri basin, thick successions of the Cretaceous rocks are exposed, which is mostly designated as Cretaceous of Trichinopoly. Now, let us talk about the Cretaceous of Trichinopoly in great detail. Extensive outcrops of the Cretaceous rocks are well developed in Trichinopoly area, where they overlie the basement gneissic complexes. It represents the oldest marine depositional event on the eastern coast of India in Phanerozoic and is flanked to the opening or is linked to the opening of the Bay of Bengal. These rocks overlie mostly above the basement gneisses and also above on the Gondwana sediments. They are overlain by Cuddalore sediments of Miocene age. They occur in Trichinopoly and Pondicherry areas. Later works have demonstrated that below the Uttur formation, two distinct units like Dalmiapuram formation and Shiv Ganga beds are also present. Moreover, Ninur formation is of the Paleocene age. The Cretaceous succession ever since it was mapped and studied by Blandford 1862 has been the focus of the attention by many, and searches by the ONGC under hydrocarbon exploration has created wealth of information of academic interest. The Cretaceous system here has been divided into three widely known groups, with Uttur, Trichinopoly and Ariyalur, and early Paleocene which is called as Ninur. Now, let us talk about the stratigraphy. The sedimentaries of the Cretaceous system rest over the crystalline basement striking northeast southwest with a Gondwana succession sandwiched between the two. The boulder conglomerate is a kind of the fanglomerate which is a fault controlled and formed by the coalescing of several alluvial fans. The plant beds show upper Gondwana affinity and rich in plant fossils or Cladophlebis indica, Actinopteris, Tilophyllum acutifolium and Electrocladus conferta. They were probably laid down in low energy conditions. The Cretaceous sediments show higher dips near the basin margin, and the faults are also found, which essentially is the reactivation of the basement tectonic lines. The mean sedimentation rate has been estimated to be 15 to 240 millimeters per year, and physical weathering was more predominant factor for the clastic material. Now, next is the Uttur Group. After boulder conglomerate, a horizon of grey shale is found which are rich in organic matter and can be a potential source rock for hydrocarbon generation. It is followed by Dalmiapuram limestone, which is essentially a sponge coral reefal algal limestone, which is composed of the remains of calcareous sponges, layered corals or microselenia, Sidaris represented by Sidaris, belemnites, bryozoans and foraminifera represented by Lenticulina macrodisca. Some of the forms are sessile benthic in nature like sponges and algae, Ethelia alba, Halimeda etc. and Selenoporaceae, and lie either as the incrustations or colonies. There are a few forms that have their shells partly dissolved by the diagenesis, but can however be identified. The faunal assemblage gives mid-Aptian to mid-Albian age and an intertidal depositional environment. The next unit in Uttur Group is a succession of yellowish to grey brown clay, often called as Karai shale or Maruvattur clay, with ferruginous sandstone and limestone bands and occasional gypsum veins. Since the dominant lithology is clay, it can therefore be identified with peculiar trellis type drainage network and badland topography. The following fossil forms along with the belemnite guards are found denoting upper Albian and mid Turonian age. Then ammonoids, coming to the fossil assemblages, of which ammonoids are Scaphitis kingianus, Turrilitis costatus, Memmitis cancellatum. Among the foraminifera you have Lenticulina cosmatina, Rotallipora cushmani. Among the bivalves you have Pecten, Electronia. Then the nanofossils are represented by Microrhabdulus decoratus and Chiastozygos littarius. Coming to the Trichinopoly group, Krishnapali Group lies over the Uttur Group with a profound unconformity and can be divided into Kulakkanatham and Anaipadi formations with a conglomerate horizon differentiating the two. Kulakkanatham shows a calcareous sandstone and ferruginous concretions and interbands of the dark colored limestone containing thick shelled bivalves. Ammonoids, rinconellids and silicified woods which are mostly drifted in nature. The next succeeding unit is the Anaipadi formation, having sandstones, siltstones and shales with fossiliferous concretions containing ionoceramids, gastropods and ammonoids, besides large tree trunks, one of which is a geological monument at Sattanur. It is 18 meters long stem of a large conifer tree giving Coniacian Santonian age. A regressive coastal environment can be suggested for this formation. Also, the hard part of a dinosaur called as Stegosaurus have been retrieved from the formation at the Sri Nattam. Next is Ariyallur Group. This group unconfirmably overlies Krishnapali Group and can be classified into 4 distinct formations that are named as Sillakudi, Kallankurichi, Ottakovil and Kallamedu formation. The entire litho package is basically a limestone band sandwiched between sandstone successions. The lower Sillakudi consists of the Arcosic sandstone and limestones with Inoceramus, Nautilus, ammonoids, echinoids and foraminifera, which indicate Campanian age. The sediments can be attributed to high energy transgressive tidal bars. The Kallankurichi succession has an unconfirmable contact with underlying Sillakudi and is a massive limestone with rudisted bivalves. This unit contributes significantly for cement industries and is mainly bioclastic packstone and grainstone. Griffia, Electronia and Lofa forms important bivalves, whereas Globotroncana ganzeri is a foraminifera found in this formation. The entire faunal assemblage gives an age of upper Campanian to early Maastrichtian for this unit. A shallow marine carbonate bank can be attributed to these carbonate units. The next horizon is a calcareous sandstone mapped as Ottakovil formation with a typical echinoid, that is Stigmatopygus elatus. The foraminifera include Globotroncana arca and Globotroncana stuatiformis, whereas the ammonoids are represented by the Pachydiskis otocodensis. Maastrichtian age is assigned to this formation on the basis of these fossil forms, and the marginal marine environment can be suggested for this unit. White to grey cross-bedded sandstone called as Kallamedu formation overlies the Ottakovil with greenish to reddish clay intercalations having reptilian faunal remains of Megalosaurus, Titanosaurus and some herbivorous forms also. The fluvial channel and overbank conditions can be suggested for this unit. Next is the Ninur formation. The Cretaceous succession is overlaid unconfirmably by a thick carbonate sequence known as the Ninur formation. The total thickness is 60 meters and can be subdivided into lower fossiliferous, middle recrystallized and upper nodular limestone. They give a significant support to the cement industry. Algal and cephalopod fossils are found, including Nautilus danicus, and that gives Danine age to the Ninur group. Coming to the climate during Cretaceous, continuing on from the Jurassic greenhouse world, climate in the Cretaceous were, if anything, even more stable, uniform and equable at very high latitudes. During the early Cretaceous, climate bands were essentially modern latitudes. Limits were found in both the northern and the southern hemispheres. Exceptions include a tropical zone largely or confined to the western Tethys, as evidenced by the widespread reef facies. A paratropical embayment reaching across the southern Europe and into the Eurasia, as evidenced by high latitude bauxite deposits, and a very large arid region, as evidenced by the widespread evaporite and calcrete deposits in southern North America and northern South America. The overall equability of the early Cretaceous climate is supported by the observation of coal deposits throughout the Pangaea and Laurasia, even in areas reconstructed as being near the early Cretaceous poles, along with the crocodile fossils about above 30° north latitude and amazingly above the 60° south latitude. The late Cretaceous sea level rise further intensified these climate gradients by creating arid belts both north and south of the tropical equatorial zone and pushing the paratropical embayment well into the Asia. However, an asymmetry developed between the north and south polar areas in the late Cretaceous. The northern polar region contains coal deposits, crocodile fossils and even dinosaur fossils well above the Arctic Circle, whereas these deposits stop at or near 60° south latitude. No doubt the fact that Antarctica had drifted to occupy a position at the late Cretaceous south pole was significant factor in the development of this climate contrast between the hemispheres. In the sea, delta O18 analyses of the planktonic foraminifera indicate that both surface and bottom water temperatures rose steadily through the lower Cretaceous, with a single strong high temperature anomaly in the upper Berriasian lower Aptian. Cretaceous marine temperatures peaked in the Turonian, that is average surface temperature of about 18°C, and then went into a rapid decline to the Campanian. The Campanian Maastrichtian interval was characterized by the strong marine surface water temperature instabilities, with several strong reversals between warm and cool phases that varied by as much as the 4°C continuing to the KT boundary. In contrast, marine bottom water temperatures do not appear to have been subject to these strong variations. Then next is the paleogeography and tectonics. At the beginning of the Cretaceous, the post-Permian breakup of the Pangaea had progressed to the point at which the northern, that is Laurasian continents of the North America, North China, Siberia and Eurasia had drifted away from the Gondwana, that is Africa, South America, India, Antarctica, Australia. Though the latter remained coherent, Gondwana was in turn separated from the North America by a narrow Atlantic Seaway and from North China by a broad Tethys Ocean. Surrounding this region of the intense tectonic activity, the Pacific Ocean occupied fully half of the surface of the planet. In terms of the continental landmasses, the primary Cretaceous event was the rifting of Gondwana near the Jurassic Cretaceous boundary, that is about 140 million years. A large rift between Africa and India formed, and propagated south until by 150 million years. Gondwana has been effectively split into two parts: South America, Africa, and India, Antarctica, Australia. Late in the early Cretaceous, about 120 million years, a rift opened up along the southern coast of Southern America, Africa, and propagated north to form a proto-South Atlantic Seaway. Early in the late Cretaceous, around 110 million years, southward propagating rifts have opened up between India and Antarctica, as well as along the northeastern coast of Australia. Seafloor spreading took place along all these rifts throughout the late Cretaceous, causing the South Atlantic Seaway to open northward, where by 100 million years it had joined with the Central Atlantic Seaway. Second is the India to drift northwards along the east coast of Africa, the Antarctica, Australia to drift southward in order to compensate for the northeastern drift of the Tethyan seafloor and the westward drift of the Atlantic seafloor. Oceanic subduction systems developed along the northeastern margin of the Tethys and along virtually the entire circumference of the Pacific plate. Pattern of the marine circulation were also affected substantially by these tectonic reconfigurations. During the early Cretaceous, trade winds blowing westwards across the Tethys Ocean would have set up a strong westward equatorial current that circled the globe. Owing to its passage between North America and northern part of the Gondwana down the Central Atlantic Seaway, direct evidence for the existence of this current comes from the similarity of shallow marine faunas from the submerged parts of the Europe and southern Asia through now submerged seamounts island systems in the Cretaceous over 1,000 miles west of the Hawaii. Aside from the circum-equatorial current, paired cyclonic gyres would have been present in the Pacific Ocean, leading to the evolution of distinctive northern and southern hemispheres, marine invertebrates faunas with continued continental fragmentation and northern drift throughout the Cretaceous. This very simple early Cretaceous marine circulation pattern would have grown more complex, especially once the South Atlantic Seaway had opened up between the South America and Africa in terms of physico-chemical characteristics. The Cretaceous is noteworthy for the number of large igneous province eruptions and the number of the large bodies or bolide impact craters that occurred during this span, as well as the large number of major marine anoxic events along Aptian, Albian, Cenomanian, Turonian, Coniacian, Santonian, and Campanian, and very small number of magnetic polarity reversal events. The long Cretaceous normal interval stretches from the Aptian to the Santonian, some 40 million years. Cretaceous rates of the weathering are inferred to have been relatively low, partly as a result of the relatively high sea levels and partly because of the relative lack of the mountain building, especially during the early Cretaceous. These, along with the proliferation of the phytoplanktons, are thought to have been responsible for elevated levels of both carbon dioxide and free oxygen in the Cretaceous atmosphere relative to the modern concentration. Thank you very much.